Hello and welcome to episode 7 of Hyperlegible, a not boring radio production. Today I'm speaking with Brian Potter, the author of Construction Physics, about a piece he wrote summarizing his nearly 5 years writing it, called 50 Things I've Learned Writing Construction Physics. Thus far, I've only interviewed people about essays on Hyperlegible, and I admit that a list is kind of cheating. But Brian has written more essays that I refer back to than almost anybody else, so this was a perfect excuse to talk to him about all of them without breaking the one conversation about one piece constraint. Why I love Brian's writing is that he goes deep into what it actually takes to build the things that I write about wanting to build. When I wrote about Base Power Company, his 4-part series on the grid was my Bible. When I wrote about QB, his whole catalogs of essays on why making houses in factories is so hard was my guide. And today, I got to talk to him about all of it. We talked about shipbuilding, batteries, nuclear, and why it is that Chicago can build skyscrapers twice as fast as New York City. One thing that I learned from him in this conversation is humility. He's gone deeper into the weeds on the topics that I write about than I ever have, both hands-on through his work as a structural engineer and through his research. And he still caveats so many of his answers by saying that he's not the expert, or that he's not exactly sure why a certain thing is the way that it is. As he writes in the piece, his biggest takeaway from writing construction physics is that there's always more to the story. And talking to him, you can tell that this is all a never-ending project to understand more and more deeply how to build the things that we want built in the world. If you're not reading construction physics, it's one of my all-time favorites, and I think that you should subscribe. I'll put the link down in the show notes. I hope this conversation gives you a little preview of why I get so much value from it. Before we turn it over to Brian, though, I want to say a few words about our sponsor. Hyperlegible is sponsored by my friends at Readwise, who build software that helps you get the most out of your reading. I've been using Readwise for years to support my newsletter, my curiosity, and now this podcast. If you like listening to podcasts like Hyperlegible, if you're a nerd who likes to listen to a podcast about essays, you'll love their Reader app. It's like Pocket, but next generation, with best-in-class highlighting, annotating, AI, and more. It also supports not only web articles, but YouTube, newsletters, PDF, EPUBs, and even X-Threads. If you want to give it a try, you can go to readwise.io/hyperlegible. That's readwise.io/hyperlegible, where you can start a free trial and get all of the articles discussed here on Hyperlegible automatically added to your account. There, you'll find articles from Tina He, Utsav Memoria, Julian Lair, Alex Danko, Parakeet, Conrad Bastable, and now you'll find 50 Things I Learned Writing Construction Physics from Brian Potter. Brian, thanks for coming on Hyperlegible, longtime fan. Normally, to kick these off, I like to ask people to summarize their essays in about 2 minutes. Obviously, you've done this as a list, the essay, 50 Things I've Learned Writing Construction Physics. So instead, I'll ask, what's the one overarching theme you've learned in the 5 years that you've been writing construction physics?
The overarching theme is that things are almost always more complicated than they seem. Simple explanations, very rarely exist. There's almost, even if the simple idea that you think turns out to be correct, there's always relevant detail and texture to the problem that will give you a much richer understanding of why things work the way they do. So it's almost always worth it and valuable to sort of dive in as deep as you can when trying to understand a topic or a problem.
So ironically, now you've tried to kind of simplify all the different things that you've written about, but then you link out to these very, very deep pieces that you've written over the years. Why did you decide to write this one as a list as opposed to some sort of essay?
The real answer is that I was working on a compressed schedule. I was going on a work retreat that was going to eat into a bunch of my writing time. And I have a very fairly specific time frame that it takes me to get something done typically, and it involves a big period of time spent reading background sources and thinking through stuff and things like that. And I just didn't have that time. So I was I need something that I can turn around much more quickly to get something out when I wanted to get it out. And so I was like, okay, well, if I base something that's based on stuff that's already written, that will cut out all the most of the research part, because it's just stuff that I already know how to do. And then, I previously had a sort of like a table of contents, a guide to sort of the stuff that the various essays that I had written, when my topics were like much more narrowly focused around construction. And I sort of got rid of that a while ago when it didn't really serve as a very good guide anymore. So I thought it would be useful to have something like that, but the list of topics is now so broad that there's not like a coherent synthesis, I think, of just every single thing that I've written. It's just it's become a much more broad scattering of topics, and so I did it in a list format. And then the last reason is just people love lists, man. That's the BuzzFeed really got that right. People love the list format. It's very compelling to people. So it shaped by the constraints that I was working under at the time.
I think you said you wrote 600,000 words so far, and I think I've read most of them. So actually having it all in a list form was a nice kind of walk down memory lane and encapsulation of a lot of the things that you've covered. What is your normal research process for a piece? You mentioned reading a bunch of stuff and trying to synthesize, but you now send out kind of your reading list. And even that is like, I read these 7 books and then here's a million different articles that I read. So like, what does that process look like for you? How long does it take? What do you read?
So typically it's kind of varied over time. For a very long time, I tried to like pretty religiously get something out once a week. And if something was like taking longer, I would just split the essay into 2 or 3 or 4 parts and just go it out one at a time.
The grid, one of the all-time best. The grid, the 4-parter on the grid was one of my favorites.
Grid 4-part, and then I had this very long multi-part piece that was comparing the World Trade Center and the Empire State Building construction processes. It was like 4 or 5 parts or something like that. I've kind of switched away from that, and I now basically just try to one-shot it and get it out all in one piece, which I think makes for better essays, but it sometimes requires a longer research process. So ideally, the process will be like, I pick some sort of topic or something I want to know about, something I feel like I don't understand, or a question I'm trying to answer, and I will narrow it down to the point that I can read basically everything that is written about the topic. And if you do a good job picking your topic, that's often a lot more possible than it seems like it would be if you pick something that's like sufficiently narrow but broad enough to just kind of still be interesting. And so I'll try to read everything that I can get my hands on about some given topic. And I say read, but for most of this stuff that I'm skimming, I have an idea of the thing that I want to answer, and even something written about, a book or a paper or something. Most of it will kind of be not especially relevant to what I'm trying to understand. So I can kind of skim through. I'm very good at skimming. And I can just highlight all the portions that I think are relevant to me and just kind of get it all stewing in my subconscious. And then once I've done that process and I have a bunch of ideas, things that I think are interesting, I'll kind of put them down a page and then try to kind of structure it into something like an outline. How do I can condense all these things that I've read, all this content, into some small, tightly bound structure that I can hang all this detail off of, basically. And then so I put together an outline, and then I flesh out the outline into a draft, and then I go through and edit the draft. And for a typical one in the realm of like 3,000 words or so, the whole process takes like a week. And so when I'm finishing up one essay, I'm starting the next one. But if it's a longer one, so one of these like 7, 8, 9,000 word behemoths, it takes longer than that, 2 weeks maybe. A lot more reading up front, and then more time to get the words down on the page.
Yeah, it does seem like you have a lot kind of already in your head about how the world works or how building things works, and then you look for specifics. How much has writing construction physics changed the way that you think about the world, and how much of it is just kind of you getting that all down on paper and finding how it applies to different areas?
So very little, I would say almost none of what I write about I knew beforehand. So almost everything that I write is the output of a research process for something that I didn't understand going into it. So anything that I've written about is usually something that I didn't really understand at all going into it. And I would say the newsletter, it's not so much an output of, what I already thought about the world. It's more a result of the kind of research process that I had. I didn't really even realize that I had this research process. And I think where it kind of came from was that before what I do now, I used to work in construction, and I worked as a structural engineer, basically designing buildings like parking garages and apartment buildings and water treatment plants and stuff like that. And what often would happen to me is we would get some job, some project, and it would be some type of building that I had no familiarity with. I never designed like a building like that before. When you're a structural engineer, you can't just like wing it, or the consequences for getting that wrong are like very, very high, right? People get hurt if you misdesign a building. People get hurt. Building could collapse. People could die. And even if that doesn't happen, if you screw up sufficiently, you could get your license revoked. So, avoiding those outcomes was always very, very important to me. And so my strategy, what evolved to sort of design these unfamiliar building projects, was to I'm just going to go look up every reference for how to design this building and, go and search for all these things, because there's design guides, published by these various industry associations for any given type of building, right? For any given thing that you're doing, somebody has already designed that type of building before, and you can go figure out, there's probably an industry association that has published a guide or a set of, advice on how to do that building. So to go through and try to find every design guide or thing that existed for a given building. And then I could anchor my decisions in like what the accepted wisdom was in how to do this thing. So I when I started writing this newsletter, I think I probably subconsciously transferred that process, where I was like, okay, if I want to not be full of shit about this thing that I'm writing about, the easiest way to do that is just go and read everything about this given topic, and then I will be sure that I'm not missing something critical. So that's, I think the newsletter has kind of evolved out of that process more than anything else.
It's funny too. I mean, when you mention being a structural engineer and kind of the stakes at hand, I think that comes across in the writing itself too, not just the research process, but like where there are things where, I'll do a bunch of research, but there are some things where I'll be like, wouldn't it be cool if like the world worked this way, where you were just going like 9 levels deep and being like, actually it works in this very specific way. And it makes sense when you're thinking about coming from a background of like, this thing cannot fall apart.
Yeah.
All right. So you conclude the piece by writing kind of something similar to what you summarize. I'm just going to read it here. My main takeaway from this list of takeaways and from writing the newsletter more generally is that there's almost always more to the story. Things that seem like recent developments often have key predecessors going back decades or even centuries. What seem like historical inevitabilities are often highly contingent products of chance and circumstance. Intuitive explanations for phenomena are often wrong. And even when they're right, the full story is often much deeper and more interesting. Causes are often complex, and what seem like simple problems often tenaciously resist solutions. So I'd love to take each one of them in turn. What are some things that seem like recent developments, but have key predecessors going back centuries or decades?
Yeah, lots of interesting examples. Wind power, I think, wind turbines being a significant fraction of electricity generation is kind of an interesting example. That feels like a very modern thing, like a post-90s thing. Maybe if you're like into the energy weeds a little bit more, like, oh, in the 80s, California built all these wind turbines, and that was the start of wind turbine construction in the US. But if actually you look back even further, wind generated electricity was actually pretty popular on like farms and rural areas in the US in like the early 20th century, because this was before there were like transmission lines out to all these rural areas providing like central station electric power. And so you would have these farms with like an electric powered windmill windmill to sort of, power the radio and stuff like that. And then what happened was a government administration called the Rural Electrification Administration. I believe it was a New Deal program, but don't quote me on that. They just came and built out all this transmission infrastructure to all these rural areas, and that basically killed the wind turbine industry in the U.S. because it was much cheaper and more convenient to get your power that way than it was from these sort of kind of rickety wind turbines. But people have been using windmills for electricity almost as soon as electricity became widely used at all. Another example, more sort of relevant to my background, is I previously to writing this newsletter, I worked at a construction startup called Katerra, and Katerra's goal was to sort of build factory built housing cheaper and less expensive than other builders could build, and kind of be like the Henry Ford of housing. And this was like, sounds like a good idea, and it sounds like such a good idea, in fact, that many people have tried to do that before. You can go back again decades, depending on how you sort of classify it, maybe even 100 years or more, and find people trying to do pretty similar ideas unsuccessfully. And yeah, there's just lots of things that look like that have this basic shape.
We're going to dig in a lot more on that idea, because it's something that I leaned on your work pretty heavily for when I've been researching it. But more generally on kind of lessons from the past, do you think that the people working on the new versions of old things more often just kind of ignore the lessons of the past, or over-index on what they've learned from the past and apply it to a situation that might not be the same anymore?
So that's a good question, because when I was working at Katerra, and I was, it became clear to me that this idea had been done a bunch of times before, and it hadn't worked. It hadn't worked any of those time. My question became, well, what's different this time? What would make it succeed where it hadn't succeeded before? And I never really got a good answer to that. And then Katerra very ignominiously went bankrupt. But yeah, it's, there's lots of ideas that like, it doesn't work, and then conditions are right, and then it does finally work. Gwern, online essayist, has a very good essay about this, where it's a book review about the MIT Media Lab, and there's all these people that like had all these correct ideas about what the future of computing and technology would look like, but they were unable to capitalize on that and become rich, because it just requires the exact right set of circumstances just at the exact right time to sort of be correct about these things. And if you're too early, you make no money at all. You just fail. And if you're too late, somebody else has beaten you to the punch. So kind of, yeah, for a lot of these ideas, you have to have the exact right timing, and it's very, very hard to sort of get that timing. You have to understand exactly when the conditions are right to kind of do it. And then just, kind of more generally, there's a very sort of increasingly widely known notion that, a lot of these, startups and just economic growth more generally is very reliant on these essentially bubbles, or like irrational exuberance, where people pour this money and investment into ideas where it maybe can't quite justify those huge amounts of investment anymore, and then it often blows up into like a huge bubble, and people are ruined. But in the result of that bubble, you have built up all this infrastructure and developed all this interesting technology, and it eventually becomes quite valuable. And so, we're probably seeing something like that with AI, where there's all this huge amounts of money getting invested in like these AI companies and building all these data centers. A lot of these people are, probably going to lose a lot of their money, but we're going to be left with like this very useful technology and infrastructure to deploy it. But if you look back again, things have predecessors. You saw something similar with like, fiber optic cable, which is this huge build out that was done before the economics could really justify it. In the late 19th century, you saw this with railroads, where people build this like huge amount of like railroad infrastructure. And then, massive bankruptcies and lost all their money, because they overbuilt it. But then we had all this railroad infrastructure after the dust settled. So you just, you're kind of dependent on these like, for your economic progress and technological progress, you're dependent on these people that are individually taking like these pretty bad bets. But at a society-wide level, it ultimately proves quite fruitful. So I'm not sure, it's very hard to sort of be rational when you're sort of making these decisions, because in sort of what steps are you should take next, or what technology is sort of ready to kind of be widely deployed, and what bottlenecks no longer exist, because in some sense the system relies on some degree of irrationality and built into it.
And now we're here talking on Zoom thanks to them laying all that fiber optic cable. So thank you to the people who lost your money in the past. You mentioned in there also the highly contingent nature of some of this stuff. Can you give an example of something that seemed like an inevitability but was really a highly contingent product of chance and circumstance?
One of my favorite examples of this is Morris Chang, the guy that founded Taiwan Semiconductor, TSMC, when he was just starting out of his career, like right after he graduated from master's at MIT, he almost took a job at Ford and wouldn't have worked in semiconductor manufacturing at all. And he only took a job at a semiconductor manufacturer, this company called Sylvania, basically by chance, because he got into this sort of dispute with the HR person at Ford because they wouldn't raise his salary by $1 a month. And he got very upset with them and took this other job at a semiconductor manufacturer out of spite. And then 30 years later or whatever, 25 years later, he goes and founds TSMC. And that's an interesting example because the model, like the idea of TSMC, where it's just like, we're just going to be a pure play foundry. We're not going to do our own chip designs. We're just going to manufacture chips for other people. That probably would have come along anyway, because just the basic idea that Morris Chang had, which is just these fabs are getting so expensive, it's getting increasingly impossible for individual companies to all have their own fabs. That probably would have the way that the industry would have evolved anyway. But it's very likely it wouldn't have ended up in Taiwan, right? It would have ended up in Japan or South Korea or something like that if Morris Chang hadn't ended up doing it. And of course, if it doesn't end up in Taiwan, the current like global geopolitical system concern looks quite different. So that's, I think, that's a sort of interesting example of how it could have ended up quite differently. The Apollo program, I think, is another example where it's sort of embedded so deeply in American consciousness that this is, we went to the moon. That's one of the things that makes the U.S. Awesome. And it feels like just like an inevitable outcome of the competition with the Soviet Union. And there's all these geopolitical forces that are pushing us in that direction. But reading about it, it seems like at the time, very early on, it was costing all this money. People were getting quite tired of it. And it does seem like if Kennedy hadn't been assassinated and that hadn't like galvanized people into wanting to fulfill this sort of declaration that he made, that maybe we don't go to the moon. Maybe we get tired of spending all this money and the program gets canceled. And then, again, things might end up looking quite different.
That one's fascinating. Do you think there's a history of the world, and maybe it just doesn't make any sense at all, but would love to hear why it doesn't make sense, because I've never thought about this idea, where Morris Chang stays at Ford and Ford becomes a car foundry? Like, it's a great man versus great idea theory, I guess.
Oh, that's interesting. Well, see, Morris Chang's ideas, they were very baked into his knowledge of like semiconductor industry. And it was just like, I know that these fabs are getting really expensive to build. I know that, and it was also baked into the idea that he knew that like Southeast Asia was like very, very good at making semiconductor chips. They had really, really high yields, like way better than anywhere else. So fundamentally baked into the proposition was that I need to go and set this operation up somewhere in Southeast Asia where they know how to make chips. So I don't know if Ford ever ends up fulfilling all those requirements, but again, who knows how things would have turned out.
Knowing that so much relies on circumstance and chance and contingency, what should people do differently? How do you live? How do you prepare for that world?
I guess my sort of takeaway from that, or one takeaway from that, is that just a very motivated person, or like a small group of like very, very motivated people, can actually have maybe ignoring reason or logic to some extent, can have like a very outsized impact on how the world works, both because because stuff is dependent on chance and circumstance to some extent, and just because so much of these big outcomes, big events, are ultimately predicated on a small number of people being like extremely dedicated and just willing to do the stuff that the other people won't do.
So this is maybe one of my favorite parts about reading construction physics, is that you kind of highlight the gap between what's intuitive and what's actually real. In everything that you've come across, what do you think has the widest gap between the intuitive explanation and the real story?
Widest is hard to know, but one big one that I think about quite a bit is with shipbuilding. And I think the model that most people have, well, most people don't think about shipbuilding at all, but the people that think about it, I think the model that they have is something to the effect of, we were really great at shipbuilding during World War II, and then after that, the Jones Act made us, even though the Jones Act came before, maybe they don't think about the timeline amazingly tightly. But after that, ultimately, the Jones Act made us bad at shipbuilding, and now we are crummy at shipbuilding. And the reality is, even before World War II, and arguably sort of during World War II, the U.S. was fairly crummy at shipbuilding in terms of like productivity. And we were basically crummy at it since the Civil War. And during World War II, we were very good at building a lot of ships quite quickly, but in very high volumes, which is like, sort of a unique, unsustainable situation. But in normal commercial operations, the U.S. was still pretty not great at it, and it was not great basically since the transition from wood to iron and steel ships in the late 19th century. And that's like 80-year difference in when sort of the U.S. shipbuilding went off the rails.
And do you think that that's mainly just a volume play that we were so good then? Is it like wartime, we drop regulations, we fund it with federal money? Like, are there things that we could do now for kind of smaller scale shipbuilding that we can take from that period to get good?
Well, so World War II was interesting because we were able to build a very, very large amount of ships, and we were able to build a very large amount of ships quite quickly, but it basically, it came at a cost. So typically you're not building this huge number of ships of the same model over and over and over again, hundreds and thousands all at once. And so when you're in that situation, you can kind of do things with your manufacturing process that you can't normally do. You can have something like series production and stuff like that. But even sort of at the peak of U.S. shipbuilding during, World War II, when the U.S. was building like, a Liberty ship every 10 days or something like that, we were still less productive in terms of like the cost and like labor hours per ship than the British were. So even in that situation, we weren't like, we were only so good at it. We didn't totally overcome the sort of naturally U.S. Standard, shipbuilding capabilities.
Why are we bad at it? Like the British you wouldn't think are much better. The British you wouldn't naturally think are much better. It's not like the Japanese or something where now you think like there's just a totally different model. Why are we so bad?
Yeah, this is a good question. I don't understand it amazingly well. The U.S. was good at building ships when ships were primarily made of wood, and they were like reasonably competitive with other countries' processes. And then when it transitioned to sort of iron and steel, U.S. shipbuilders were kind of reluctant to make that switch because they felt like Britain is so good at making iron, they're so good at making steam engines, they just have this insurmountable advantage in sort of the factors of production at building these ships. Our wood ships are still getting better. We already kind of know how to build these things. And then the U.S. had very strict, that's one reason why the Jones Act is not a major sort of the deciding factor is why U.S. shipbuilding is so crummy. It's because even before the Jones Act, the U.S. had very strict Jones Act-like laws, which restricted, what sort of countries' ships could go between U.S. ports. And so they were already operating in a fairly protected market. And the U.S. sort of historically, it traded a lot more with itself than with other countries. And so, U.S. ships could go up and down the coast and up rivers, and that was a pretty big market for ships. And so the U.S. Shipbuilders just didn't feel especially compelled to compete very hard, I think which is not really an answer, but it kind of gives you the basic a shape of the problem. And then because those cabotage laws, those Jones Act like laws were in place and have always been in place since the early 19th or late 18th centuries. That situation has just never really resolved itself. And now there's all these other factors of scale and cheaper labor elsewhere and cheaper inputs and stuff like that make it very difficult, perhaps impossible to sort of overcome.
Makes sense. And last one from this very rich paragraph. What's a problem a lot of people think is simple that is actually really complex?
Yeah, so this is a problem. One example I'll go with is something that I spent a lot of time in the early years of the newsletter writing, which is the problem of construction productivity, which is just, we don't really get any better at building buildings in terms of like hours it takes to produce them, in terms of the cost, per square foot of building or whatever. None of that gets cheaper. Most stuff that we build over time, we sort of figure out how to ways to build it, cheaper and faster and better. And that doesn't really happen with construction. And I think, again, this sort of intuitive explanation people have for this, which is why companies like Katerra got started, was just, we need to figure out how to build this stuff in factories, because building in factories is what makes things cheap. And once we can figure out how to do that, we can sort of make these buildings cheaper. But really, it's a little bit more complicated than that. And really, it's not just, the act of doing something in a factory. Just doing something inside a big enclosed space doesn't magically make it cheaper. It's just there's specific things that are possible inside a factory. And if you can do those things, have economies of scale, or automate and have very, high volume production and stuff like that. That's what makes it cheaper. And it turns out that with construction, even if you do your work in a factory, doing the specific things that a factory makes possible to make stuff cheaper is quite difficult. And so it's very difficult to make your construction more productive and cheaper just by doing it in a factory.
Yeah, we're going to dig in a lot here. Like I said, I wrote about a company called QB. I referenced your pieces that I'd read in the past, and reading again, you, I think, spend 21 of your 50 kind of slots in this piece on construction. And so it's a rich vein. It makes sense that you can't magically just go to a factory and then things, just because you're under one roof, get cheaper. But I thought you had an interesting kind of comparison. Why is prefab construction not cheaper than conventional on-site construction, but manufactured and mobile homes are?
So this is a good question. And I will say, I don't feel like I have an amazingly great answer for it. Like, I feel like I don't understand it amazingly well. I understand a lot of the pieces, but I don't quite know how they fit together. So one answer is just that manufactured homes are targeting sort of a lower end market, and they use sort of often use like lower end, less nice materials, and stuff like that. And so that's part of it. And another part of it is that a manufactured home is very good and very inexpensive if the smaller it can be and the more it can be in like a single unit. So manufactured homes come in like single wides, which is just basically like one single unit, and then double wides, which is 2 units put together. And then you can even go to like triple wides, which are 3 units, and then sort of more complex things. And as you go up in size and complexity, the difference between conventional construction and manufactured homes starts to shrink. And so once you're getting into sort of a triple wide with maybe a garage and a porch and all this other stuff, that difference has really, really been whittled away. So part of it is just there's certain form factors that, manufactured homes are able to build in, that you can build that stuff quite inexpensively. But as you sort of get more complex and you move away from those specific form factors, the advantages really disappear. But more generally, the difficulty of prefab construction is just you often can't really save all that much money make your process all that much more efficient by moving it into a factory. And there's a lot of other costs that you incur in the process of doing that. So in terms of savings, you can't really, even if you move your stuff into a factory, it's hard to sort of have your factory build things in really high volumes, partly just because the market for homes is not amazingly big, and you're shipping into sort of a relatively small catchment area because it's too expensive to ship this stuff too terribly far, because homes are just so big. You can't ship them all that far while still being sort of cost competitive. And then there's other sort of costs that you incur too. You have to break your house into a lot of different pieces, and then you tend to add costs and things like connectors to sort of stitch those pieces together. And you have extra probability that something go wrong. And it's, when you're building these factory built modules to sort of stitch them together, you have to have, more quality control. And if you have to fix a problem, it's much more expensive to sort of fix the problem when you have these factory built components and stuff like that. So there's all these additional costs that you incur. I know some guys who worked at a company that tried to get into the sort of prefab modular construction, and they sort of abandoned it after it didn't go well. And they came up with the idea of the prefab tax, or the modular tax, where there's all this other additional stuff you have to do with modular construction that makes it more difficult and more expensive that you don't have to do with conventional construction. And in general, it's just hard for the advantages that you get from doing stuff in the factory have historically not really been enough to offset that in a lot of cases.
And all of that said, reading your kind of reflections on your experience at Katerra, it didn't seem inevitable that it was going to fail, right? Like there was a bunch of stuff in your piece that was like decisions got really slow and we became a big organization, or it seemed like the CLT bet just didn't work out the way that you thought the CLT, or they thought the CLT bet was going to work out. Like it seems like there were avoidable things that in retrospect, maybe Katerra would have worked had they done stuff differently. Taking all those lessons, like if you know, you had to solve this problem. If your job, the president appointed you, you have to figure out how to fix this by starting a company. What would your approach be?
This is not the most interesting answer in the world. My approach would be, somebody writes me a check for, $500 million or whatever. I would take that check and I would sit on it for 10 years, 15 years, 20 years until automation and robotics are good enough that you can basically completely automate the on-site construction process. And then that would basically solve the problem. That's, for if nothing else worked, if you can replace, a carpenter making $50,000 a year with a robot that costs $5,000 or something like that, that essentially solves your problem, right? And so I would wait, just wait until the automation gets good enough. If the check is really big, if I have a $5 billion check, maybe you can actually do the work to push that automation forward.
I think Masa wants another shot.
My answer. That is the most straightforward way I know that would basically solve the problem of construction productivity.
That makes sense to me. Why does Chicago build skyscrapers twice as fast as New York City? I did not know this before I read this.
Yeah, I didn't know it either. Yeah, it's good. It's a good question. I don't have I'm not super confident in my answer. My general sense is that New York has a lot of very burdensome building rules that make it really expensive to build there. So there's all these rules about unions. Yeah, lots of major cities have unions. I don't know if Chicago does or not. But I think the building unions in New York are particularly burdensome in a lot of ways. There's all these rules about safety that end up being burdensome. All the, scaffolding. I think they have very stringent scaffolding rules and stuff like that can often make it difficult. As I understand it, you can't really build with like a tower crane in New York. So you have to use these other smaller, less good cranes to kind of get your buildings built. And so there's all these difficult rules that make it just especially difficult to build in New York compared to a lot of other U.S. cities. And Chicago is the only other city other than New York that really builds appreciable number of skyscrapers. So it's not so much New York versus Chicago. I think it's New York versus most other places in the U.S.
And then you blow my mind in the opposite direction by saying that in terms of building high profile skyscrapers, the U.S. is actually as good as China, as fast as China, as good as China. What's going on there? Yeah,
this is also very surprising to me. This is another thing. I feel like I'm adding this caveat a lot. It's like, I don't really know the answer. And the reason I gave that sort of stipulation that it's high profile skyscrapers is because this is based on data from this website called the Council on Tall Buildings and Urban Habitat, and it's a big database of essentially most major skyscrapers that are built in the world. But I don't think that database really tracks all these like the huge numbers of like residential apartments that get, China puts up, 100 of like identical buildings, that are all this like residential concrete high rise. And they're not as far as I know, they're not really tracking those. And the ones that are in there's not like super great information for. So it wouldn't surprise me if like those types of buildings, they can get built quicker or whatever. But so for like high profile, which means like the big stuff that gets like, tallest in the world or more than 80 stories or something like that. Yeah, they're fairly comparable. And I don't have an amazingly good answer. One possible part of the answer is that in general, construction developers often seem to value speed of construction a lot less than you might think that they would. And this is another thing that I don't understand like amazingly well. But you would think that it's like for most things, if you have a situation, if you're building something, you maybe have like a lot of like fixed costs or overhead bound up in the building of that thing. And so if you're not producing something, you're still losing money because you're not spreading your fixed costs out, or you're incurring overheads without getting money back in from selling the widget or whatever that you're making. And in construction, that's a little bit less true. Your costs are a large in part labor and materials. And if you're not building something, you're not incurring those costs. That's not like, that's not totally true, because there's overhead costs, there's general conditions and construction loans and stuff like that. But historically, it's I've observed that just developers just often don't seem to be amazingly concerned about getting stuff built super quickly, at least, modern day ones. If you go back historically, that becomes different.
There's been an empty lot across the corner from my house for, I think, the 4 years since I've moved in, and now it makes sense. They're just incurring whatever costs, they don't have to pay for labor and materials. And so it's just going to be a rat infested empty slot on the block for a while. But speaking of high overnight costs, let's move on to energy, because this is one of the areas, again, that I've leaned on you a lot for. Like I mentioned, loved the grid piece, but talking about nuclear and a bunch of other stuff. And I think in your energy category, the most interesting question for a lot of them ends up just being kind of why. I think there's probably a lot behind those. So to start, why did the US start adopting gas turbines after the 1965 Northeast blackouts? And did that adoption accelerate their becoming economical?
Yeah, so with gas turbines, it's interesting because it's an idea that people have had for like a really long time. You can find like people sketching out like gas turbine ideas since like the 1700s or something. But to get a gas turbine to like produce a useful amount of energy, you need to have a pretty efficient compressor and other sort of components like that. And it just took a long time for those compressors to get efficient enough and good enough that you could like extract a useful amount of energy from a gas turbine. And it wasn't really till like World War II that kind of started to be true. But with the 1965 blackout, what happened, there was this huge blackout all through the Northeast in the US. And I think a gas turbine was actually used. I should have looked this up before this interview, but so I'm 70% sure that a gas turbine was used to like sort of kickstart the grid back into operation after the blackout. And it turns out that gas turbines are like very good at like starting a grid from what's called a black start, when you just don't have any power at all. And so a lot of utilities bought gas turbines as basically like an emergency measure in case of a major blackout. And that ended up being the a big initial use of these like industrial gas turbines. But it was really what really accelerated gas turbine adoption was this law in the 1970s passed by Carter called PURPA, which basically was the law that forced utilities to buy small amounts of electric power from like private producers, and sort of there was the first major thing that like kind of broke the utility monopoly on electricity. And so then when the law was structured in such a way that they were only required to buy power in certain conditions. And one of those conditions was if you provided both heat and electric power, combined heat power plant. And a combined cycle gas turbine, which generated electricity and also heat, and then recaptured that heat to generate more electricity, qualified under PURPA. And so you started having all these small operators, non-utility operators, start building these combined cycle gas turbines, and that's what kicked off combined cycle gas turbine adoption in the U.S. As far as improvement, it was really kind of just along many decades of just incremental improvements. They slowly got better, they slowly got cheaper, and then eventually you had this sort of instigating events that made people suddenly start to adopt them for specific uses in large numbers.
Chance and circumstance. Why does Oregon have the second most planned electricity generation after California?
This is a very good question. I don't really know the answer. This is one I really don't know the answer to, and I do not have a good theory. I know they have like a lot of like hydroelectric power and stuff in sort of the up in that part of the country. So I don't know if they're like buying buying this these power generation, gonna like plan on sell it to other states more broadly. I don't know. I really don't know this one.
All right. You write that the US has about 10,000 times as much energy storage capacity for hydrocarbons as it does for grid scale electricity. What do you expect to happen to that ratio over time, and how?
Yeah, so that's an interesting interesting question. And it kind of depends on like how different technologies evolve and like their comparative rates of improvements. If batteries continue to get cheaper, I expect them to get coupled with new solar PV deployments more and more, and probably wind turbine deployments as well. And so I expect battery capacity to really continue to increase quite a bit. The amount that it will increase, I don't really know. Is it going to get 10 times more, 100 times more, 1,000 times more? I don't have a super good sense of that. For that you need to talk to like a real energy expert that understands all this modeling and stuff like that really well. But so I expect batteries to get more deployed, but then depending on how certain technologies work out, you could see a decline in hydrocarbon use. You could see a steady state or increase in hydrocarbon use if some of these scenarios where people think, well, solar PV is going to get just incredibly cheap, and the best way to take advantage of that is to use this incredibly cheap solar PV electricity and just synthesize synthetic fuels, right? And then just take advantage of all the hydrocarbon infrastructure that we already have. And so if that ends up happening, you could see maybe we need even more hydrocarbon storage. If we need to double or triple the amount of the energy that the U.S. uses. So I don't know. It depends on sort of how some of these other technologies continue to evolve.
Both batteries and solar, and specifically solar, are like the poster children for learning curves. You write the kind of learning curves can stop, and you can't take them for granted. What stops learning curves?
The big thing is just embedded in a learning curve is just the idea that like there's possibilities to sort of improve this process or improve this technology. And if those possibilities just kind of aren't inherent in the technology or whatever it is that you're doing, then your learning curve can only kind of really go so far. And the example that I use to sort of point to this is like titanium, which has improved on like a learning curve like fashion, but it hasn't fallen down the learning curve very far. And a big part of that is just the process that used to produce it is this chemical process called the Kroll process. And it's really not, it's not the idea, it's not the process you would ideally choose if you had your druthers as to how you could make a given material or given chemical. I'm not a chemical engineer, but I get the sense that it's kind of involved. It's like a batch process. It's hard to, it's kind of difficult to do. It's kind of hard to keep the titanium from getting contaminated and stuff like that. And so it's just, there was hope, for a long time they would find some sort of better process to make this material, and that they really just haven't found one. And so you're stuck with this sort of kind of crummy process to make something. There's only so much that you can kind of squeeze out of that. And then another big thing is just it's kind of the structure of the product that you're offering. And so there's a very good paper, I don't remember the name of the authors, but it breaks down energy technologies into sort of different categories based on what sort of kind of learning curves that you see. And the stuff with the best learning curves is stuff that is like, can be manufactured in really, really large volumes and has sort of a uniform structure and doesn't really need much custom adaptation to the specific use or the specific site or something like that. So something like solar PV, where you can just make 100 billion identical modules in factories is very amenable to sort of learning curve stuff. So you can just scale up your factories and get huge economies that way. And making the same thing over and over, you can improve your process and reap the benefits of that over a large amount of output. If your thing requires a large amount of like customization and adaptation to like specific circumstances, it's much harder to reap the benefits of learning curves and have really large learning curve style improvements. So any sort of like major like construction project type thing kind of falls into that category.
The promise of SMRs and kind of new nuclear is we're going to take it from a construction process to a manufacturing process, and we're going to come down the learning curves. You talk about the fact, though, that the U.S. Navy follows many best practices for nuclear reactor construction, such as design reuse, but this hasn't been sufficient to make nuclear power cheaper than other forms of ship propulsion. Why? Do you think nuclear is fundamentally just resistant to learning curves, or is this possible to get them on that learning curve?
Yeah, that's a good question. And so a lot of, I've said that like 4 times. That's a good question. Wow, every question is a good question. Part of that is just that construction project thing. And then I think with nuclear especially, it has some unfortunate negative economies of scale where stuff gets like, typically with like something like a power plant or like a chemical facility or something, you get pretty good economies of scale due to geometric effects as you make your equipment physically bigger, mostly due to like area volume relationships. You make a tank that's like twice as big and it does not take twice as much material to make that tank. And nuclear plants are sort of major, big chemical handling facilities in some sense. And so a lot of power plants, like coal plants or whatever, they will show these like nice economies of scale, but making them bigger and bigger to a certain point. But with nuclear, there's some sort of unfortunate negative economies where as you build your plants bigger and bigger, the risks become bigger and bigger. And so you're required more burdensome safety systems to sort of prevent those risks from coming to pass or whatever. So the risk of a meltdown from like a big nuclear plant is much, much higher and much larger than a much, much smaller reactor, where if the reactor is small enough, as I understand it, you really can't have a meltdown at all because there's just not enough heat generated. So that's, I think, a big part of it, is that you kind of have these sort of like negative economies of scale in nuclear plants. And then just in general, there's, with most things, it's like, we built this thing and we had some problems and we then fixed the problems, and it works better. But with nuclear, everyone is so worried about the risks of radiation that, we built this thing and we figured out there might be some problems, and then we had to like change everything how we do about this construction to make sure that we never have anything resembling those problems again. So every new, improvement comes with this like new ratchet of regulations and overhead that makes everything more difficult. So it's just, again, people are fundamentally very worried about nuclear safety, and then it just bubbles up into all sorts of difficulties with building this stuff. And U.S. naval reactors are very similar in that sense. People are very worried about radiation leaks, and so they're built to a very high standard of safety, and that just makes it hard to sort of build this stuff cheaply.
Yeah, it's funny how many similarities there seem to be with your kind of shipbuilding and Jones Act story, where you blame the Jones Act, but all the seeds were planted before. Same with kind of 3 Mile Island or even the NRC and kind of nuclear. There was, the over ordering of nuclear plants, and it was a utility killer. And Jane Fonda was like, all these things kind of happened, and then you get 3 Mile Island, and then you get kind of the NRC. And so now you're in a spot where people are scared, but then you put regulation in place, and now it just gets so unbelievably hard to build, even if you wanted to get back on the learning curve, that it seems like a tough situation, but a lot of people are taking different approaches. And so, fingers crossed and optimistic.
Yeah, it's on my list it's perpetually on my list of things to like look into small modular reactors, because I really haven't spent much time learning about it and I don't understand it amazingly well. But yeah, historically with power plants, geometric scaling, you're just making them bigger and bigger and bigger, has been a pretty important way that electricity has gotten cheaper. And so I'm not, you're with a small modular reactor, there's like a trade-off there. You have the benefits of like series production, where we're going to make, 50 of these, and the 10th one is going to be cheaper than the second one or something like that. But you're trading off some of those geometric benefits. But again, as I pointed out, you're also trading off maybe some of these safety requirements as well. So it's not amazingly obvious to me what that looks like on the balance. So that's kind of one of the reasons that I eventually want to look into it when I have the time.
I'm going to put my vote in if there's a voting process for the SMR piece. I cannot not wait to read your take on it. I know we're Coming close to time here, I have a bajillion other questions, but I'm just going to give you a couple more that are that really kind of surprised me. One is that the number of U.S. bridges in critical condition actually declined by 70% between 1992 and 2023. And you said that U.S. interstates are roughly as good as other countries. Why do people think we're so bad at these, and what have we actually gotten right?
I'm not sure. I think part of the reason why people think that we're so bad is that there are a lot of things that the U.S. is legitimately quite bad at. In general, the construction stuff that the U.S. is best at is stuff that is a single family home or resembles a single family home. And then there's certain other things, industrial facilities, we're probably pretty good at. But a lot of stuff, the more that something requires a lot of government involvement and oversight, the worse that the U.S. tends to be at. So there's a lot of things that just we are legitimately quite bad at. The things that we're better at, homes that we're good at building, stuff like that.
Two more just rapid fire ones before I go to my three closing questions. What did Cambridge and Bell Labs get right in terms of Nobels?
Cambridge, I don't have a good sense of what went right there. It's the U.S. is the U.S. today is sort of in a position that that Britain was at the late 19th and early 20th century, where maybe a falling industrial power, but it's very, very, very strong in science. In the U.S. in UK was just very, very good at science in the late 19th and early 20th centuries, and Cambridge has just been very good for very long. As far as Bell Labs was able to hit this very difficult spot to hit, where it was able to take a very, very extremely long-term view of what was valuable research and stuff like that, and fund this highly speculative stuff that might not pay off for years or decades or whatever, because they were sheltered under the wing of a government monopoly. But they also were pretty careful to make sure that the stuff wasn't just totally blue sky, totally disconnected from anything that could ever make a profit for the company. So they had this whole army of special engineers and managers that would subtly redirect the efforts of all their researchers to working on stuff that it was likely to be promising, even if that promising payoff was in a long term in the future. They kept them on track to doing the stuff that would likely have some sort of commercial benefit. A guy named Eric Gilliam, he's written a lot about research organizations and what makes a good research organization, and he spent a lot of time researching Bell Labs, and he describes it. I'm going to sort of screw up his phrasing, which is better, but it's they have a long yard but a narrow fence, where they had a lot of freedom to explore different research avenues, but that was directed in a pretty narrow way to the stuff that was likely to have a good payoff. And so they were able to sort of hit this relatively narrow target, and existed in a realm where they could afford to just spend money on this stuff for a very long time, because they were just this huge, enormous, company monopoly. So they had a lot of, it was a sort of special confluence of circumstances that are quite difficult to repeat.
Last one that I'm going to go right at your list on, and then just three easy ones. So thank you for putting up with this just onslaught of
Oh yeah, you're fine.
Why have jet engine and commercial airliners always been so expensive to develop?
This is another thing that I don't really understand amazingly well. The nice thing about being able to write about kind of whatever I want to is I can just dip in and out of the various topics as they catch my interest. But the downside is, a lot of these things I'm not an expert on. And even after reading quite a few books on a topic, that still doesn't make you an expert. With jet engines, it's just it's this combination of needing really high levels of performance. They have to, these jet engines are operating at really, really high temperatures. Everything has to be made to a pretty high level of precision. It has to be really, really reliable to kind of be safe. And that's just that's always just been those three things, and have been kind of difficult to achieve simultaneously. And with with commercial aircraft, commercial jet aircraft in particular, I think it's somewhat similar concerns where it's just hard to make these things reliable and safe and fuel efficient all at the same time. And it just takes a lot of investment to kind of make that happen.
All right. So now the easy stuff. What's one other essay of yours? There's a bunch of great ones linked here. I think people should read all of them. But if you had to choose one other essay of yours that people should read, what is it?
It's funny. The most, there's a contrast. The stuff that I like the most is not necessarily the stuff that is the most popular. And the most popular stuff is not the stuff that's necessarily in my wheelhouse. I was looking at it the other day, and I think the most popular essays are all stuff that is written about like airplanes and aircraft. So like, building airplanes in World War II, titanium, airports, how to build a jet engine, all that stuff is very near the top, but that's not necessarily my background. And then the stuff that I like the most is often stuff that is other people do not necessarily seem to be amazingly enthusiastic about it. So I recently wrote a piece about diamond drill bits and how the technology has sort of evolved over time and what it tells us kind of about like learning curve improvements that I was really happy with. And I learned quite a bit, but it didn't make a huge amount of waves. Another one that I personally really like is exploring the early anti-growth movement in California, which is another, example of something that feels like a concern of today's times, but is really something that has very deep roots. And sort of you can see a lot of the same, anti-building NIMBY type concerns that we're constantly dealing with today take place and take shape in California in like the late 50s and 1960s. I think exploring those, really gave me a better understanding of why we have these sort of anti-building movements and why they're so sort of difficult to do. If I had to pick one, I'd say how to build 300,000 airplanes, building airplanes in World War II, which is quite popular and a lot of people like.
Awesome. Yeah. Again, read the whole catalog. I think my favorite has to be the grid series. I just thought it was amazing. But and I've linked to it in a few different pieces. So if you haven't read it already and you're listening to this, go read that and go read how to make 300,000 airplanes. What's one essay, or you can choose book because you've read so much as part of your research process. Like, what's one that you just loved that you think other people should read, an essay or a book?
There's this essay. It's written. I don't remember the guy's name, John something, but it's called "Reality Has a Surprising Amount of Detail," and it's just about like for any given thing that you are trying to do, actually accomplishing it will require you addressing and coming to face with a lot of specific nitpicky details. If you don't resolve these specific nitpicky details right, you'll be able to not be able to accomplish the thing that you are trying to accomplish. And this applies to basically no matter what you are doing. And reality is rarely as simple as would be convenient for us. And there's always sort of complex, nuanced of things that are important to take into account. So I think that one is quite good, and it rhymes with a lot of the things that I conclude in this sort of 50 things that I've learned piece as well.
Yeah, normally I would ask you for the one sentence takeaway, but you kind of gave it there, and we've talked about it throughout that the reality has so much complexity. So I guess the question is similar to one I've asked about something different earlier, but knowing all of that, knowing that reality is so complex, what should people do? Like, how do we go fix the world? How do we go build new things, understanding that there's so much complexity and detail out there?
I think the sort of most straightforward answer is just remember that stuff is detailed. Remember that simple answers usually aren't so simple. Remember that the world is complex, and don't get caught up in the sort of simple, easy, comforting explanations for things, and be willing to sort of put in the work to understand how stuff is, how complex stuff really is, and have the humbleness to recognize how much that you don't know and how much for any given topic you still probably need to learn about it before sort of drawing conclusions from it.
Well, Brian, thank you so much for teaching me some of those details through your writing over the years and letting me appreciate that lesson even more. And of course, thank you for doing this with me today. This was fun.
Yeah, thanks for having me.